Okay, so this is number two question, right? This is number two question. So look at the question very well. Because of time, I will also wipe. So I can use the board to solve. So I'll wipe the question. Have you seen the question? It was a body at rest is given an initial uniform acceleration of 6.0 meter per second square for 20 seconds, after which the acceleration is reduced to 4.0 meter per second square for the next 10 seconds. The body maintains the speed attained for 30 seconds. They calculate maximum speed, number one. Number two, total distance traveled during the first 30 seconds. Number three, average speed during the same time interval as into above. So from here, we start a calculation. We together now. So wipe and start a calculation. So wipe from here, wipe from here. Are we there now? Wipe from here so I can get the diagram. Once you get the diagram, we are good to go. Okay, so here now, in this case, I'll read from here. It said a body start from rest. So first of all, I'll get my like this. Like this. Are we together now? I'll get it. Remember, here is my V, meter per second. And there is my T, is always what? Time. So the body starts from rest. Before then, I cannot solve this question because they say a body starts from rest with an initial acceleration A given to us to be 6.0 meter per second square. That is A. That is A1. Then A2 is 4.0 meter per second square also. But remember that it is reduced. At this A1, what is the time? At A1, T1 is equal to 20 seconds. 20 seconds, right? Then T2 is equal to 10 seconds, right? 10 seconds. So here, remember, it is velocity time graph, not acceleration time graph. So we must convert all these ones to a velocity before we can use them to sketch. If we don't convert them to velocity, we cannot solve. If we use it like this, it is wrong. So we must bring them to velocity before we solve. And remember that A, acceleration is equal to V all over T. Is it true? This implies that V I'm looking for is equal to AT. Then, so here V1 is equal to this, which is what, 6 times 20, giving me 120 meters per second. Then for here, V2, using the same formula also, is equal to 40 times 10, giving me 40 meters per second. So I've converted all these ones to velocity. Now I've moved them from acceleration to velocity. But there's something they say. They said after which the acceleration is reduced to 4. So acceleration is reduced to 4. Reduction means when it is reduced means this one was 120, then it was reduced. So in this case now we're going to remove something, right? So the reduction will now be, so this V2 now, the normal V2 now will now be V2 will now be equal to, what do you have there? 120 minus 40, giving me 80 meters per second. You understand? So this is now 80 meters per second. This is not the reduction. Are we together now? So if I'm to sketch now, watch. So a body at rest, I'll write 0 here because at rest. With an initial uniform acceleration for, so this is it. From here, are we there? From here to here, then here becomes, here is my 120. 120. Are we together now? Good. It's reduced. This is reduced. Reduce like this, right? It's reduced. We reduce it. So from here becomes my, if you reduce, what is remaining? 80. Here is now my 80. Are we together now? Then it says maintained, the speed is maintained. Now at this point here, the time this one maintained, time here is what? 20 seconds. So read it right. Then the time of this deceleration here is what? 10. 20 plus this is 30. Plus 10 is 30. And he maintained this thing, this one. He maintained it. You maintain it to this point, right? To this point. This is the point. It didn't come to right. They stopped there. They say it maintain it to this point. Then for the next 30 seconds. So 30 plus 30 give us here is what? 60. So this is how it is. There is nothing like come to rest. It doesn't come to rest, right? So remember that if you are giving acceleration, you have to convert it to velocity before you solve. So this is the velocity calculations here. Then we represent it in the diagram. So this is the journey of that body from 0 to this point. It moved like this, then it's reduced and maintain a uniform speed and stop. This is it. It did not come to rest. Are we together now? So this is the one it accelerate. This is the one it come down. Then here is the time at which it maintained the uniform speed. So we have this like this as the diagram. So the next thing now is for us to now solve the calculations given. First question says, okay,